In the previous segment, we looked at stationary distribution and we looked at different ways to compute the stationary distribution. And we motivated the study of stationary distribution with a problem drawn from big data applications. And we're going to revisit that problem, and we're going to apply the notions that we have studied in order to be able to solve that problem. So just to remind ourselves, we're given a list of celebrities, and they're ordered according to their popularity. And there's some natural phenomenon at work by which these celebrities, their popularities get reordered one step at a time. And so this is a very dynamically changing order. And more formally, every time step, two consecutive celebrities are chosen uniformly at random, and their popularities are swapped. So the less popular one becomes the more popular one, and vice versa. And we're interested in keeping track of the most popular celebrity. Okay, and we looked at a very simple algorithm. We maintain the best celebrity C, and every time step we probe a random celebrity and check with the celebrity C. And if there's an improvement in the randomly probed celebrity, then we update C. A natural question, therefore, is how good is this algorithm? Because it's nice, it's a very simple algorithm, it doesn't have much of an overhead, but we want to know how good this algorithm is. In particular, we want to find a value k with which we can make this guarantee. We want to show that the celebrity that we output at any point in time is a top k celebrity with high probability, meaning the probability of the form 1 minus 1 over n for some small integer k. So we want to be able to say that, well, if we output a celebrity with high probability, that celebrity is going to be in the top k of the list. Okay. So we're going to assume that there are n celebrities, and just to be clear, the celebrities are ranked from rank 1 being the most popular to rank n being the least popular. And let's use the letter C to denote the rank of the celebrity, capital C, output by the algorithm at any point in time. Okay, so the C keeps changing, so it's quite natural to view this as some sort of a stochastic process. Okay, in some cases the C can be reassigned to C plus 1. Okay, when will this happen? Well, if C gets reassigned to C plus 1, that means the celebrity that we are outputting has actually gone down the list. Okay, it has become worse, has become less popular. When will that happen? Well, it'll happen when the natural phenomenon chooses that celebrity C and the next less popular celebrity, and then their popularities were swapped. So then this happens with probability something like 1 over n. Sometimes, however, we can get lucky and C can be catapulted to a better rank value. So it can be improved something from 1 to C minus 1. Okay. When will that happen? When we probe, we do a random probe every time step. If that randomly probed element, celebrity, has a much higher popularity status or is a more popular celebrity, then this sort of an improvement will be seen. Okay, so what we're going to do is we're going to design a Markov chain that captures these notions, and we're going to be a bit pessimistic. Okay, and we're going to design the Markov chain so that it doesn't exactly capture what the algorithm does, but in the sense that if this Markov chain, we can claim something about this Markov chain, something good about this Markov chain, then the same thing can also be claimed about the algorithm. Okay, and this Markov chain has to capture two things. It has to capture both the random phenomenon by which your C value can increase to C plus 1 as well as the algorithm's effects, whereby a randomly probed celebrity ends up being much better, and therefore the C value gets catapulted to a much better value. Okay, I'm going to make some simplifying assumptions. This is where we're going to be a bit pessimistic, but nevertheless simplifying but safe assumptions. Okay, uh, we're going to assume that the random phenomenon can only increase the value of C. So that is, it can only affect us in the negative way, where C becomes C plus 1. Because the random phenomenon can also help us, but we're simply going to ignore that. Okay, and at any time step, when the random phenomenon succeeds in making C go from C to C plus 1, there's also the possibility that the algorithm may be able to correct that. Not only correct it, can be actually improving the C to a much better value. But we're simply not going to allow that to happen. So in that sense, we're going to simplify the Markov chain to where if the random phenomenon underlying popularity phenomenon swaps C and C plus 1, then there's no improvement that we see. Okay. Under these assumptions, we're going to design the Markov chain. And the states of the Markov chain are simply going to be the values that C can take. Of course, if C can take 1, which means it's the highest ranked celebrity, and it can take the value n, which means that it's the lowest, it's pointing to, capital C is pointing to the lowest ranked celebrity. And in this Markov chain diagram, we're only showing the transitions from and to C. So there's many transitions we're not showing. If you are at C, when the random phenomenon affects you, you go one step backwards. And that happens with probability 1 over n. Okay. And alternatively, you can be catapulted to a better position. Okay, and that will, let's look at the probability with which you'll go from C all the way to state 1. That's going to happen with probability 1 minus 1 over n times 1 over n. Why is that? Well, the possibility of making any step forward happens with probability 1 minus 1 over n, because with 1 over n probability you're going to move backwards. Okay, and given that you're not moving backwards, that's this 1 minus 1 over n probability, then you move all the way to 1 with probability 1 over n. Now with this same probability, we will also be able to transition from C to 2 and C to 3 and so on up to C to C minus 1. Let's denote the stationary distribution, the vector pi, to be pi 1, pi 2, and so on, up to pi c plus 1, and so on, up to pi n. And of course, pi c will be the probability that the Markov chain will be at state C well into the future. So we're interested in the steady state behavior of the algorithm, and that's what pi c will be, the probability with which the Markov chain will be at state C. So let's compute this stationary distribution. Let's start by computing pi 1. Okay, pi 1, we're going to compute that by looking at the cut between state 1 and the rest of the states. So the rest of the states, we're going to call that a single virtual state S. And if you look with when we are at this, when we view it this way, from this virtual state S with probability 1 over n, let's begin by computing pi 1. In order to compute pi 1, let's consider the cut between state 1 and rest of the states. Now the rest of the states form a single virtual state S, and we so in that sense this Markov chain looks like the two-state Markov chain that we've already looked at in the previous segment. Okay, Okay, so pi1 is the stationary distribution of being at state 1, and pi s is the probability with which we'll be in any of the other states, and that's equal to just the summation of the other probabilities. And if you're in state 1 with probability 1 over n, we'll be transitioning to state 2, which is essentially virtual state S. And if we are in any of the states in the virtual state, then with probability 1 over n, we will be transitioning to pi 1. So simply using the cut method, we will get pi 1 equals to a half. And this is something you can verify. Now that we know pi 1, let's look at how to compute pi c for some arbitrary c. Okay, so again we're going to consider the cut between states 1 to c minus 1 and then states c to n. Okay, so now let's look at the transition from left to right, or rather from right to left. So this is right to left. Okay, and these pi n minus 1 up to pi c are the probabilities with which we'll be in any one of these states, n minus 1 and so on up to c. And then for each one of them, with this probability 1 minus 1 over n times c minus 1 over n, we will be transitioning into the left side. And we're treating the whole left side as one virtual state. So we don't know where we will be transitioning into, but we'll be transitioning into one of the states in the left side. And that should be equal to, and notice while you're going from right, or rather from left to right, you cannot transition from any state in the left to a state in the right. You can only go from c minus 1 to c. Okay, so that's why here we only have pi c minus 1, and then the probability that we'll actually make that left to right transition is 1 over n. And here, if we work through this and make some simplifying assumptions, so for example, all these probabilities are going to be greater than 0, and so we simply ignore them and make this an inequality. And we continue to solve this to get pi c to be less than or equal to n minus 1 over n raised to the c minus 1 times 1 over 2 times c minus 1 factorial. Okay. Let's make a quick observation before we proceed. These pi c values, they decrease as c increases. Okay. And what is as a consequence, if we find the c value, if we find the c value such that pi c is at most 1 over n squared, we're done. Because we don't want a very large c value, we want as small a c value as possible. But if we find a c value where pi c is 1 over n squared, all subsequent values of pi c are only going to be smaller. And by the union bound, if you add up all of their probabilities, it's not going to exceed 1 over n. And so then the probability mass has to rest on all the states that preceded c, which is what we want. So that's going to be the c that and that gives us the k. Basically, the c will get k. Okay, so with that being the case, let's try to solve for that c. So we set instead of pi c, we set it as 1 by n squared, and on the right hand side we have the expression that we have over here. And if we solve it, make some simplifying assumptions, we will eventually find the value of k. So let's go through that. So this quantity using 1 minus x is roughly equal to e to the minus x when x is close to 0. We can use that to and approximate it to e to the minus c minus 1 over n, and rearranging we get this approximate equation. And notice that it's okay to overestimate c, because we just want it's okay to be a little bit pessimistic. Okay, so what we're going to do is, in order to get a way to find out c, we're going to ensure that we're going to throw away some terms, but in that process we're going to ensure that we'll only overestimate c. So in the left hand side, we're simply going to throw away some of the terms. So now c minus 1 factorial, so we're just going to retain this one term. C minus 1 factorial is less than or equal to n squared. Okay, and what is that equal to? Well, again we're going to do a little approximation on the left hand side, which will ensure that we'll only overestimate the value of c. So we're going to write c minus 1 factorial as c minus 1 by 2 raised to the power c minus 1 divided by 2. Okay, and that's at most n squared. And now taking log, we get c minus 1 by 2 times log c minus 1 by 2 is at most 2 log n. Okay, and again we're going to throw away this term in order to get c minus 1 is at most 4 log n, or in other words, c is O of log n. So what this says that the algorithm with high probability is going to output a celebrity that's within the top O of log n list of celebrities. So that's the upshot of this claim here. Of course, we've been fairly sloppy about the way we came up with this bound. So there's possibility that we can be a bit more careful with the analysis to get a better bound. So that will be left as an exercise for you.